We are looking at systems of linear equations. Let's look at a few examples. Look at this first one here. 8a minus b equals 9. 4a plus 9b equals 7. So two equations, two unknowns. You're trying to find an a and a b that solve both of them. Next to it, we've got three equations, 1, 2, 3. There are three variables. You want to find an a, b, and a c that will solve all three of those things. Similarly here, I've got three equations, three unknowns. Here, two equations, two unknowns, and we're looking for a x and a y. If I have two linear systems, what happens is we have two lines. And if I have two lines, my two lines might intersect in one common point. And if that happens, I'm going to get one solution. We say that that is an independent system. If I have two lines and they happen to be parallel, then they're never going to intersect, which means I'm going to get zero solutions. This is an inconsistent system. And here you might say, well, what happened to your two lines? Where's the red one? Well, the blue one is sitting exactly on top of the red line. And so they are intersecting at every point. And so there are an infinite number of solutions. And we say it is a dependent system. Now, when you get to three equations and three unknowns, all kinds of complications can occur. Each of your equations are equations of a plane. So you might have three sheets of paper that never intersect. You might have two of them parallel and then the other one cuts through, but all three of them don't intersect anywhere. It is possible, though, that I could have one plane, another plane, and finally a third plane where they would all three intersect in exactly one point. Now, these were linear systems. We also have nonlinear systems that we're not going to look at. But you see here, I've got the intersection of a circle of radius 5, and I've got a parabola, and they intersect in two places. I could have a circle and a line, and the line intersects the circle in two places. And I could have all kinds of strangeness. I could have an ellipse intersecting with a hyperbola, and I'm intersecting in four places. So when it gets to nonlinear things, all kind of strange behavior can happen. All right, in question 1, we're going to use a technique to solve this system of two equations and two unknowns by substitution. I pick one equation and I isolate one of the variables. Now, you typically pick an easy one. Now, it doesn't matter which one, you just pick one. And then I'm going to substitute it into the other equation and solve. So here I looked at my two equations and I see y is by itself there. So I'm going to pick this equation. I'm going to move the 2x to the right, and I get a relationship involving y. I put this into y in the other equation. So right here is y. So if I distribute the 3 in and I start simplifying all that, I finally get down to minus 2x equals minus 8. Divide both sides by minus 2, and I get x equals 4. How do I get y? Well, I've got this nice formula here for y. I just plug in what I just learned about x, and I've got minus 8 plus 12, and I get y equals 4. And you can check x being 4, y being 4. If I plug them in, it solves both equations. So these two lines intersect in one common point. Another method for solving systems of equations is to use the addition method. In the addition method, I'm going to add the two equations together and see if I'm lucky and if a variable cancels. 9x add 2x, nope, no canceling. 6y added to a minus 12y, nope, no canceling. So if not, then I multiply one or both equations by something so that a variable cancels. So I was noticing here I've got this plus 6y and I've got a minus 12y. So I'm going to take this equation and multiply it by 2. So an 18x 12y minus 24. All right, so I add them up, and when I do, the y's are going to cancel now. And I get 20x equals minus 40. Divide by 20, and I get x equals minus 2. To get y, you substitute this into either one and find out y. So I picked the top one. 9 times minus 2 is a minus 18, plus 6y is a minus 12. Move the minus 18, and I get 6y is 6, or I get y equals 1. So these two lines do intersect in one point. We do have one more method, and it uses matrices. And what is a matrix? A matrix is an array of numbers. All right, so in this case, I've got this square bracket thing, which is a matrix. It has 2 rows, it has 3 columns, and so we say it is 2 by 3. This matrix has 1, 2, 3 rows, but 4 columns, and so it is 3 by 4. In general, a matrix looks like the following. I've got the top row, which is row 1, row 2, row 3, row I, and finally row M. And you see the numbers that are inside there. The first number says what row it's in, and the second number says what column it's in. So this A22, whatever that number is in the second row, second column. So for example, if A looks like this matrix, then 3 is in the A11 position, minus 4 is in the A12, first row, second column, and also the same for row 2. All right, in question 3, we begin to do some row operations. So I've got my matrix here, and with this matrix, I've got row 1, row 2. I'm going to take 1/3, multiply it by row 2, and make a new row 2. All right, so 1/3 times 0, 1/3 times a minus 9, and 1/3 times a minus 3. And so this is my new row 2. So this is the new one, new. And so I then fill it in. All right, what if I take in question 4, 1/3 multiplied by row 2. I'm going to add that to row 1, and I'm going to make a new row 1. The little arrow tells you what the new row is going to be. This multiplication is only temporary. All right, so 1/3 times row 2, 1/3 times 3, 1. 1/3 times -6, a -2. And 1/3 times a -9, I get a -3. I'm going to add that to row 1. So 1 plus 4, 5. -2, add 5, 3. 3, add a -3, 0. And that is my new row 1. All right, let's see question 5 here. We have a bigger matrix. Let's see. I need 2 times row 1. All right, what is that? 2 times 4, 2 times 3, 2 times 5, 2 times 5. And that's what I get there. I'm adding in row 2. All right, so 4, 2, 5, 2. And I'm going to add them up, and I'm making a new row 2. So 8 plus 4, 12, 6 and 2, 8, 10 and 5, 15. 10 and 2 is 12. All right, so just fill it in as my new row 2. Any other multiplications are just temporary. All right, so what kind of row operations can we do? Well, I can, if I want, I can swap some rows. So you see here they have taken row 2 and swapped it out with row 3. That's allowable. I can multiply a row by any non-zero number. I can add 2 rows together and make a new row. So these are what we are allowed to do. You might say, well, why are we doing that? I'm glad you asked. So in questions 7, 6, we are using the matrix method to solve this system of equations. So we start off by grabbing all the coefficients, 2, 7, -15, 1, 4, -12. Where the equals is, I write a vertical line. And this is my matrix. My goal is to do some row operations to it. I'd like to make it look like 1, 0, 1, 0. And if I can do that, then I'm going to automatically get the answer for x and the answer for y. Now you might say, what are these numbers you've got around there? Well, that's the order. I want to get this 1 first. I want to use the 1 to make a 0 under it. I want to get a 1 here third, and finally use the 1 to make a 0 above it. All right, so I'm looking. I've got a 2 there. I don't have a 1, but there's a 1 there. So I'm just going to swap out row 1 and 2. Okay, so just swap them. Now, I would like to use that 1 there, and I would like to make that under it a 0. How do I do that? Well, seems to me if I take -2 times that 1, I get a -2, and -2 add 2 would be 0. All right, so I'm going to take -2 times row 1, add it to row 2, and I'm going to make a new row 2. So let's see, minus 2 times the whole row. Let's see, minus 2, minus 8, and a minus 2 times this minus 12 is 24. I'm going to add that to row 2. All right, so here's row 2. Add them up, and I get 0. I get a minus 1, and I get a 9. And that's my new row 2. All right, where are we? I got a 1, got a 0. I need a 1 there. I've got a minus 1. You typically make ones by multiplying or dividing. So I'm going to take and I'm going to multiply row 2 by negative 1. That's pretty easy. So 0, 1, minus 9. All right, we're almost there. 1, 0, 1. I now need to use this 1 to make a 0 above it. All right, so let's see. I think minus 4. So I'm going to take minus 4 times row 2, add it to row 1, and I'm going to make a new row 1. Let's see. Minus 4 multiplied all the way across row 2. I get 0, minus 4, and a plus 36. I'm going to add row 1. Let's see what happens. I get 1, 0. 36 minus 12 is 24. And so that's what I get. I get a 1, 0, 1, 0. Therefore, the answer for x is 24, and the answer for y is minus 9. All right, and question 7. All right, so let's see. Similarly, I want to use this matrix method called Gaussian elimination or Gauss-Jordan elimination. So what do I do first? I grab all the numbers. Minus 2, 15, 6, 3, minus 12, minus 9. Yep, got that. Equals become the vertical line, and again I'm trying to get 1, 0, 1, 0, and then I'm going to get the answer for x and y. Well, I'm looking at this thing and I don't have a 1. I need a 1 in that top position. Now you could divide this row by minus 2, but then I'm going to make an ugly fraction. So I probably don't want to do that. Luckily here, I'm looking at this one and I see if I divide by 3, I'm not going to get any fractions. It's going to divide nicely. All right, so I'm going to go ahead and just swap out rows 1 and 2. So I did that. I'm going to take row 1 and divide by 3. And I do that. And now I have a 1. All right, same thing as before. I want to use 1s to make zeros. So I think 2 times 1, yeah, that would make a 0 under it. So 2 times row 1, 2 times row 1. So do that. I got that there. Add that to row 2. Yep, I see all my numbers. Add them up, and I get 0, a 7, and a 0. All right, so I'm going to fill that in. That is my new row 2. Where am I at? 1, 0. Oh, I need a 1 there. All right, so I'm going to divide row 2 by 7. All right, so I get 0, 1, 0. So we're almost there. I now need to use this one to make a 0 above it. So I'm thinking 4. 4 times 1. All right, so 4 times the whole row. So 0, 4, 0. Add that to row 1. Okay, add them up, I get 1, 0, minus 3. And so, looks good. I've got a 1, 0, 1, 0. And so the answer for x is minus 3. And the answer for y is 0. Now, looking at that, that's what I'd like to have happen. So here's my matrix for my 2 equations and 2 unknowns. I'd like to make 1, 0, 1, 0, and then I'll get my answer for x and for y. But it could happen that in the process, I end up with a row where I get 0, 0, and something not 0. What that tells me is my system of equations has no solution. They will never intersect. They are parallel lines. And if in the process of doing row operations, I might get a whole row of all zeros. If that happens, then actually I'm looking at the same line. One line is sitting on top of the other one, and I have an infinite number of solutions. Now, if things get bigger, supposing I had 3 equations, works the same way. I get a 1, I make 2 zeros under it. I make a 1, I get a 0 above it and a 0 below it. And I make a 1, and then I use it to make 2 zeros. And if I can do all that, then my 3 planes actually intersect in one common point. And I get my answer for x, y, and for z. The 3 equation case is doable. It just takes longer, and you have to be extremely careful because it's easy to make a multiplying or adding mistake.